Okay, so this last unit for us is in some ways kind of the simplest, not just because we're talking about gases, which are the simplest form of matter, but also because by this point in time in the semester, conceptually speaking, we have either encountered these concepts already, or we've encountered concepts like them already. And so it's not necessarily that we are dealing with, super new material here, or even old material, but we're dealing with a lot of related stuff. And so it becomes important for us in that context that we kind of figure out where we are and how best to proceed. And so from that standpoint, we need to talk about what makes gases different than the other phases of matter. And so one of the things that we can kind of point at as far as, especially in a comparison to liquids and solids that we saw last week, the lack of definition for gases is one of the really unique characteristics of those gases. In liquids, we could talk about the fact that a liquid had a defined volume, that we had enough crowding and intermolecular force existing between those liquid molecules and each other, that they would at least take on some kind of defined volume. And in solids, we can talk about the fact that those intermolecular forces were strong enough that they actually caused the solid to have a shape. And that shape was defined and rigid and kind of immovable in some ways. Gases are the exact opposite of this. They are structureless. They will fill the shape of their container regardless of how big the container is or what shape it takes on, because those molecules are so far apart from each other that they really have no interaction with each other. And so as their container grows, it just grows with it. So the first thing that we're really going to look at out of this module then is we want to define what gas properties are and put them into context of some kind of key principles of gases. And so what we're describing here is something called the kinetic molecular theory. Now, the kinetic molecular theory is a theory, a series of statements that governs what we expect gases to behave like. And in particular, we are talking specifically here about what are called ideal gases. When we describe an ideal gas, what we're really describing is how we expect gases to behave. Now, when we get to the end of this module, we'll talk about circumstances where gases don't behave this way. But for the most part, we're going to talk about ideal gases. Ideal gases are those that perfectly follow the kinetic molecular theory. And so there are some key ideas in this. First of all, we can make a pretty fundamental assumption that relative to the size of their container, gases tend not to have much in the way of size or volume. So what this first idea allows us to do is it allows us to say that the volume of a gas is the same thing basically as the volume of its container. Why is that important? Well, when we go to start using gas laws to try to predict certain kinds of properties of gases down the line here, it's a lot easier to talk about gases if we just can talk about their containers. I have a 3-liter balloon. I have a 2-gallon gas tank. The volume of the container being the volume of the gas makes it really easy to kind of parse that out, as opposed to going, okay, well, the container's 3 gallons, but the volume of the gas molecules itself is probably about a half a gallon. So I've got to think about, it's more like 2.5 gallons of space instead. Because those molecules are so small relative to the size of the container, we can kind of forget that they exist, at least at the molecular level. The kinetic molecular theory also talks about the idea of temperature and kinetic energy. Now, we've already kind of covered this in other places, but the basic idea is that we know that when the temperature increases, so does the kinetic energy. Now, this is a concept we have seen before. We saw it last week when we were talking about the idea of vapor pressure, a liquid overcoming its intermolecular forces based upon kinetic energy. Also related to something that we saw last week, the idea of intermolecular forces. We can consider the intermolecular forces of gases to be negligible. Now, what does that mean? Well, spacing. One of the key features of intermolecular forces is that those molecules had to be close enough to each other to attract each other, right? The closer they were to each other, the more of those attractions that we could form. Well, in these samples of gas, we don't have that kind of attraction, because the spacing here, even for these molecules that we'd say, oh, they're kind of close, they're only kind of close temporarily. So they really don't have intermolecular attractions to each other. London dispersion forces, dipole-dipole forces, those don't really apply, at least not in the gas phase. The last key idea is about collisions. Now, for those of you that are taking physics or have taken physics in the past, you've heard this concept brought up before, the idea of an elastic collision. Elastic collisions are those where we've got two things that are interacting and they basically bounce off of each other and energy is perfectly conserved between them. This is as opposed to an inelastic collision, where in an inelastic collision, some of that energy of combination gets lost to friction, to heat energy, to sound energy. There are attractive losses along the way. And those losses add up or manipulate how we would view those collisions in a conservation of energy kind of standpoint. We know energy is conserved, but where is it conserved? When we talk about elastic collisions, like the ones that we see in gas molecules, the energy is conserved within the molecules themselves. So even if I have an object coming slowly and another object coming quickly, all that means is that there's going to be an energy transfer from the fast object to the slow object. The slower object's going to move faster, the faster object's going to move slower as a result of that collision. No energy is going to be lost internally to heat, light, friction, whatever. One of the relationships that evolves out of this kind of distribution and interaction of these gas molecules is the concept of molecular velocity. Now, because we have these gas molecules, because they are in constant random motion, we're going to find that even though they are spaced far apart from each other in general, we are going to find that they do collide with each other and with other objects frequently. As a result of all of these different collisions that are taking place, within a gas sample, we might have gas molecules at several different velocities at the same time. Some might be going really, really fast. Some might be going kind of slow. Some might be kind of in the middle. There is an equation that describes kind of the probability distribution of these velocities. It's called the Maxwell-Boltzmann equation. Notice I did not put it here on the slide. In no way I'm going to ask you to calculate it. But what's important for us to pull out of here is that this diagram, this graph, shows us something. And what it shows us is that this is the relative distribution of what kind of velocities we would expect out of a sample at a given temperature. So here's my curve at 25 degrees Celsius. The average velocity would be this value right here. The root mean square velocity is something we'll talk about in just a couple of seconds. It's always a little bit higher in speed, and it's accounting for the fact that there's a few more molecules over here with that given speed that's a little bit higher. What's important to note, though, out of this distribution shifts if we shift the temperature. So if I go from 25 degrees, I get this distribution. If I go to 1,000 degrees, I get this distribution. And the distribution showed by this red curve, notice that its net velocity is faster than what we expected at the 25 degrees. Now, it's not nearly as tall, and what that tells you is that there's a greater variety of velocities at 1,000 degrees than there are at 25. But the net average has shifted to faster. Now we can quantify the root mean square velocity, the kinetic energy of a given gas, using this equation here. Now, one important thing about this equation, I'm not actually going to ask you to calculate root mean square velocities at any point in time. The reason I've given you this equation is to help us to establish some qualitative relationships between some of these variables. So 3 and R, those are constants. Don't worry about those. T, absolute temperature in Kelvin. Already kind of talked about this idea. If my temperature increases, my velocity is going to increase as well. That's all that this relationship is really telling us. If I increase the temperature, I'm going to see a shift in the velocity toward faster, because now those molecules have more energy, more energetic molecules move faster. We kind of, again, something we've already known, we just now have an equation that kind of relates it for gases. I want to pull out this other term, this term in the denominator here, m sub m. This is the molar mass of that substance, the molar mass of that gas. And notice that it is not a direct relationship like temperature is. Temperature is in the numerator of this fraction. As part of the numerator, we know that if it increases, the root mean square velocity increases as well. Molar mass is in the denominator of this equation. As a part of the denominator, we know that it's actually inversely related to that root mean square velocity. So what does this mean if we're comparing gases? Well, it means that if I have a heavy gas, it's going to move slower than a lighter gas. The bigger the molar mass is, the more it's going to drag down that root mean square velocity. And that brings us to our first interactive question for today. Not that one. There we go. I have two gases here, methane and oxygen. I want you to put them in the proper order from least to greatest velocity. So whichever one is the slowest should go on top. Whichever one is faster should go on the bottom. Right, assuming that these two gases are at the same temperature, then it comes down to a matter of molar mass. And to that end, if I am comparing CH4 versus oxygen, the molar mass of methane is 16.05. And the molar mass of oxygen is 32. So we know from the Boltzmann root mean square that heavier means slower. So the slower gas would be the oxygen, and the faster gas would be the methane. And so that's the order that you should have put them in. Oxygen first, then methane, since we're going in order of speed. Right. The next thing that we want to start looking at is a concept related to pressure. So other than velocity, how can we start to describe gases? Well, one of the ways that we can do it is pressure. Now, from a standpoint of kind of like a physics perspective, pressure is simply the force over a unit area. So units in physics are usually things like, newtons per square meter or newtons per square centimeter or something along those lines. We're not going to use those kinds of units, for one, because for gases, that puts the values really, really, really high. And second, we want to think about this more conceptually. From a conceptual standpoint, pressure is more about collisions. So when we talk about the number of collisions in a sample increasing, we usually talk about the pressure increasing as well. When we talk about the number of collisions decreasing, we talk about the pressure decreasing as well. So as those molecules are moving around in their container, We know that they bump into each other. They also bump into the walls of the container. And when they bump into the walls of the container, that force that gets exerted in that collision, that is what we can measure as pressure. Pressure is most commonly defined by the atmosphere. So 1 atmosphere of pressure is defined as the pressure at sea level for the atmospheric gases. Now, that doesn't do us a whole heck of a lot of good because we are rarely at sea level. So what are some other ways that we can measure pressure? What are some other conversions that we can do? So I'll give you some things that are common. So in the laboratory, common units of pressure would include millimeters of mercury and torr. Now, one thing that you should notice about both of these units is that they appear to be the same, and that's because they are, in fact, the same unit. Why do we have 2 units to describe the exact same measurement? History. This goes back to the barometer. The barometer was invented by a man by the name of Evangelista Torricelli. His barometric scale used, you guessed it, millimeters of mercury. Sometime later, not sure how much later, sometime later, the unit of millimeter of mercury was renamed in Torricelli's honor as the torr. And the millimeter of mercury was used because that was the unit he used on his barometer. So they are the same unit. The use of torr to describe it came significantly later as kind of a historical homage to his contribution to the field. Now, where might we see some of these other units? Pascals or kilopascals. This unit here, this tends to be a physics unit. Why do we see that unit used in physics? Well, because that's the unit that's based on newtons and meters and kilograms and the kind of the standard scientific units. Why don't we use it? Well, you can see here, 1 atmosphere of pressure is 101 kilopascals, which means it's 101,300 regular pascals, which means that if normal atmospheric pressure does that, anything beyond that, just the numbers start getting ridiculous. So we rarely see pascals used unless it's in a very specific kind of circumstance, or we're talking about things that are low pressure kinds of circumstances. You know, maybe we're using a vacuum jar or some kind of low pressure environment. These bottom 2 units, these are common American units of pressure. Inches of mercury, this is the kind of unit that we see a lot in weather forecasting, where we can talk about atmospheric pressure is 29.35 inches of mercury and falling and raising. It's what meteorologists use to help as one of the patterns of predictive behavior. PSI, this tends to be pounds per square inch. This tends to be what we use for gauge pressures. So we're measuring pressure on tires. We're measuring pressure in terms of, in your fuel box. Those are usually PSI that are used. Gas tanks use PSI, although you'll see a lot of gas tanks use PSI or thousands of millimeters of mercury as their gauge units. Next problem for us to take a look at here. We fill our bike tires to a pressure of 75 psi. what is that in torr? So to answer this question, we need to go back to a very simple mathematical concept, the commutative property. All of these pressure units are all equal to 1 atmosphere. So by the commutative property, by the transitive property as well, if one is equal to the other, they're also equal to each other. So I want to turn PSI into torr. They're both equal to 1 atmosphere, so I can make them equal to each other. 760 torr is equal to 14.7 PSI. So with that in mind, a conversion like this is actually pretty easy to do. I just pulled the values off of the table. 760 to 14.7. So 75 multiplied by 760 divided by 14.7. My initial value was only in 2 sig figs. So I'm going to have to round my 3,877 accordingly. So 3,900 torr would be the appropriate value here. All right, any questions with pressure conversions? All right, then let's look at some, let's close up here today by looking at a couple of simple relationships related to gas laws. So the first law that we are going to look at is something called Boyle's law. Boyle's law gives us the mathematical relationship between pressure and volume. If the amount of gas and the temperature of that gas are held constant. Now, from experience, we know qualitatively the relationship between pressure and volume. Take a balloon. You blow it up and you tie it off. You have held moles of gas and temperature constant so long as you don't move that balloon around from cold areas to hot areas. Now, if you take that balloon and you squeeze on it, try to get it to be smaller than it is, the balloon fights back on you. Why does it fight back on you? Because as you're trying to compress it, the pressure inside of the balloon is increasing, and it's going to push back against you because of that increased pressure. Now, inverse proportionalities like this, where one increases and the other one decreases and vice versa, we can express those using products. So Boyle's law from a mathematical calculation standpoint looks like this. My initial pressure times my initial volume is equal to the pressure at the final condition times the volume at the final condition. And this is a direct relationship, but in reverse. So if I increase the volume by a factor of 2, the pressure goes down by a factor of 2. If I increase the volume by a factor of 3, the pressure goes down by a factor of 3. It's a direct relationship, but in reverse. That's what it means to be inversely proportional. The second relationship that we want to look at is something called Charles' law. Charles' law concerns the relationship between temperature and volume. Again, this is something that you have seen before. We've talked about the idea of thermal expansion and thermal contraction. This, on the other hand, is a direct relationship. There is no inverse property here. As temperature increases, volume increases as well. Now we can get into the whys here, talking about collisions. When we increase the temperature and increase the energy, what happens to the collisions? Well, they're going to increase as well. We talk about the idea that increased collisions leads to a greater pressure. Well, in this case, since pressure is being held constant, that extra energy has to go somewhere. So it can't go to increase the pressure. It must go to push out on the volume of the container. And that's what happens. Direct relationships are matched by quotients, not products. So if I want to look at the relationship between volume and temperature, I want to look at this as a ratio of conditions, not product of conditions. The big kicker here, the temperatures have to be in Kelvin. They have to be in Kelvin. Can't not be in Kelvin. And why they can't be in Kelvin, or they can't not be in Kelvin rather? Well, first of all, it has to make sense. If I put 0 degrees Celsius in either of these denominators, you know as well as I do, you can't divide by 0. That's one obvious factor. If I put a negative in either of these, I'm going to end up getting a negative on the other side as a consequence. Negative volume doesn't make any sense. But even beyond that, let's say that we're looking at beyond just those kinds of what the Kelvin temperatures will do, they give us a better representation of the relationship of the energies. That's why we have to go to an absolute scale. We're talking about energy here. A 10-degree sample and a 20-degree sample, they aren't as far apart in energy as you think. The Celsius scale would have you believe that the 20-degree sample is twice as energetic. It's not. It's maybe less than 1% more energetic, 2% energetic. Not nearly as big of a difference. So we've got to take that into consideration. So when we use this equation, it's got to be Kelvin temperatures down here. One interesting side trip here about the Charles law. Charles law is actually one of the ways that we were able to first estimate absolute zero. If you remember back to one of the first activities that we did in lab this semester, it was a graphing activity. One of the graphs that I had you make was this one. Now, we didn't call it Charles' law at the time. I just said it was a volume versus temperature graph. But the graph was this graph, in fact. And if you forecast that graph down to where the volume is equal to 0, that's where we get our absolute zero temperature at negative 273.15. It's an extrapolation. We're able to measure all of this. You can't measure that directly, but we can imagine that if it's linear through this point, it's probably linear all the way down to the end. And that's how we came up with the value. Let's do a couple of gas law practice problems, and then we'll call it a day. So looking at this first one, we've got liquid nitrogen. We take a balloon that is 2.6 liters at 19 degrees Celsius, and we put it into liquid nitrogen. Liquid nitrogen has a boiling point of negative 195.8 degrees Celsius. The question is, what is the volume after we put it into that liquid nitrogen. And so to do that, we need to set up Boyle's law. I've got PIVI is equal to PFBF. Now, the 2.6 liters, that's my initial volume. Oh, you know what? I'm wrong. Shame on none of you for saying anything. There's no pressures in here. This is a temperature problem. I'm using the wrong gas law. Since we're talking about volume and temperature here, I need to use Charles' law. VI over TI is equal to VF over TF. Now, the key attribute of this particular problem, my temperatures have to be in Kelvin. So 19 Celsius, 19 plus 273 is 292 Kelvin. My negative 195.8 Celsius is going to give me 77.2 Kelvin. So plugging those into this equation, my initial volume was 2.6 liters. My initial temperature was 292 Kelvin. I don't know what my final volume is. That's what I'm trying to figure out. But we're getting it all the way down to 77.2 Kelvin. These kinds of gas laws are an exercise in relatively simple algebra usually. So to get VF by itself, I need to multiply each side by TF, 77.2 Kelvin. Right-hand side of the equation is going to cancel everything but VF. Left-hand side of the equation, Kelvin is going to cancel. Everything else is going to multiply or divide together to give me liters. 77.2 times 2.6. Divided by 292 to two significant figures is 0.69 liters. All right, one more practice problem. This one is, in fact, a Boyle's law problem. So PI VI is equal to PF VF. My initial volume is 20 milliliters. My final volume is 5. And my initial pressure is 0.826 atmospheres. So 0.826 atmospheres times 20 milliliters is equal to PF times 5 milliliters. So 0.826 times 20 divided by 5 to two significant figures, 3.3 atmospheres. Yeah. When the numbers are nice and even like this, it's actually really easy to see the relationship. So this contracted by a factor of 4, which means the pressure is going to go up by a factor of 4. So this times 4 gives us 3.3. All right, any questions with gas laws? Okay, so there are more of these coming, but that is a different question for a different day. When we come back from Thanksgiving break, We're going to talk about some of the more complex gas laws, including ones where we see multiple variables changing at the same time, not just one at a time. And we'll also get into some applications when we get into talking about chemical reactions involving the gas phase as well, which means, yes, stoichiometry is coming back for one last ride. Have a great weekend.